In this lab, we will be visiting the topic of electrochemical cells. So this has to do with electrochemistry. Specifically, that is chapter 17 from your OpenStax textbook. We will be using several equations from this chapter, notably just your standard cell potential equation using standard values. And then we will be also practicing some cell notation, and then also using the Nernst equation. So that is whenever you have non-standard conditions. So why are electrochemical cells important? So batteries are actually all electrochemical cells. So what they do is they harness the electrons transferred during this redox reaction that is occurring, and they're using that to generate voltage. So in a redox reaction, you have oxidation and reduction occurring at the exact same time, and you can view it as a combination of half reactions. So, oxidation is one half reaction, reduction is the other half. So an electrochemical cell overall consists of oxidation half cell and a reduction half cell. And this is what this picture is showing here. This is showing you an overall, circuit that is plugged into this voltmeter here, which is generating a voltage, and you have the complete circuit. Now, if you want more details on how this electrochemical cell is working, just more details on it and understanding exactly what's going on here with the electrodes and the salt bridge and everything in the phases, definitely visit my pre-recorded lecture video on electrochemical cells. So I go in depth on there. But essentially here you can see the circuit, how it's a complete, circuit. I know I'm repeating myself. But on one side you have your oxidation, and this is your anode side. And then on the other side you have your reduction. So these are both your half cells joined together with something called a salt bridge. Now, how do we relate this back to chem, or how do we show this like as a chemical equation? So your molecular equation, it's showing you your solid electrode, your ions in solution, and then also the ions on that salt bridge as well. You can take out your spectators essentially, and then you end up with a net reaction. This net shows you overall the ions that are participating, the ions and the solid elements that are participating in the actual reaction. So again, if you need to brush up a little bit more on electrochemical cells and also cell notation, I do have 2 videos on that in my pre-recorded just lecture video. So that would be in the folder in your lecture material on the course site, where we have everything for electrochemistry. Of course, if you can't find it, I can also help you find that and get you that link. Okay. So another topic that is important in this lab, or understanding, it's important in understanding to complete this lab, is standard reduction potentials. So this is a very common way to evaluate relative activity of metals to compare their standard reduction potentials. So this is the voltage that's produced in a half cell under these very specific standard conditions. So 298 K, 1 molar, and 1 atmosphere condition. So you've actually heard about these standard conditions in, several times before, maybe in Chem 1 when we were discussing gases, and also during the enthalpy, so the thermochemistry chapter. So you've probably heard of these conditions here or there. But these are the standard conditions we're referring to. And this voltage measured under these conditions is what produces our standard reduction potentials. And these are all relative to the standard hydrogen electrode, which we use the acronym as SHE. And that potential is defined as 0. So essentially it's like we have a baseline, and anything else we're comparing to that baseline, and that's where these standard reduction potentials for a variety of half cells come into play. In terms of what these values actually mean, so these less active metals, the lesser active metals have a positive value of your standard cell potential, indicating that these cations like to take electrons more than hydrogen cation. So they're more easily reduced. So the more positive this value is, positive, the more easily reduced. So you see how it's showing you potential, right? Something with a higher potential, it's going to be more easily reduced. And then you can also look at it in the lens of like oxidizing agent, and things that are really easily reduced will be good oxidizing agent, because that's what they are. Anything that gets reduced, if you want to label what the agents are, what got reduced is the oxidizing agent, what got oxidized is the reducing agent. So that's why you can view it in this lens as well. So these are those values that I was discussing. So I should have had that figure on there, but so these are the standard cell potentials measured for each of these types of cations. So notice that it's all these cations and they are all gaining electrons, and you can see the values associated with them. And remember, we said the more positive, the higher the potential, meaning the more it likes to get reduced. It likes taking those electrons on. Okay, so here we're back to that net equation that we showed at the very beginning, right? And this net equation had to do with this electrochemical cell that we're displaying here. How do we actually calculate the overall standard cell potential using these standard values that already exist? So right here, what's happening is we are physically measuring it with a voltmeter, and we're getting an experimental, in other words, an empirical value, right, that you're measuring in the lab. But what if you already have these values and you just want to calculate it, or you want to compare it to that calculated standard, values that already exist? So what you're going to do is you're going to use this equation. So you can calculate it by taking the standard cell potential of the cathode and the standard cell potential of the anode, and you plug it in, and then you can get the value. Notice how this value is very close to that. So, some slight differences are just due to the voltage going through the wires and just some physical limitations in that sense. But if you do need to revisit how to calculate this, there's also multiple videos in our chapter folder related to electrochem, where you can revisit those videos and refresh on this, because I'm just doing the very fast version of this. And finally, we have the Nernst equation that we're going to be using. So what we were just talking about was standard cell potential. So at those standard conditions, right, they require 1 molar and partial pressures of 1 atm. But what about the cases where you don't have those concentrations or pressures, right? That's where you use the Nernst equation. And you can calculate it using your standard value, your standard potential value. This is just like a constant in this equation, so you subtract away this part right here. So this is just a value. You divide by the number of moles of electrons that are being used to reduce whatever cation you're looking at, and then you take the log of the Q. So you will take the concentrations, you will calculate Q, so products raised to whatever they need to be raised to over the reactants. Okay, so there are kind of a few moving parts to this. So I have linked a video on how to calculate these non-standard cell potentials, and it's within the procedure. Just to be very clear, to receive credit for your sections, you will need to either take a picture of your work showing all the steps for a sample calculation. You do not need to show the calculations over and over and over and over. and then you will insert those pictures with your work right under, where you're reporting those values, or you can scan the work and upload it as a separate file or attach it like at the end of this lab. However it is that you wish to attach, but as long as it comes with your work. So we have two parts to our procedure and data collection. So notice that here in this lab, I did kind of mesh together procedure and data collection just because I'm going step by step so that it's kind of easier in terms of reporting and in the both different tables. I don't want you to complete the procedure and then come back to the tables and be like, I don't know what's going on. So I kind of just took it step by step and put everything together. So it's like data, but also procedure, right? So everything's kind of together. So part one, we are comparing measured standard potentials to calculated potentials. So what you're going to do first is construct a few cells, and then you will calculate their cell potential values from already existing values. So I'm going to show you in this video on the next slide exactly how the website looks, how the virtual lab looks, and we will go from there. Okay, so when you load this screen, that's how it will look. It's a very simple screen in comparison to your previous virtual labs that you've been working with. But so I'm going to be flipping back and forth between your actual lab and the screen so that you kind of know what point I'm discussing and exactly what you're doing. So if we're constructing each of these cells below, we are measuring and recording the voltage for each cell in table 1, column 1. Okay, so how do we do this? So we're working with this cell right here first, right? So this is zinc on your anode side. And like I said, if you need some refreshing on cell notation, visit this. I will make sure to link the correct video, but either way, visit the cell notation video in the Electrochem lecture videos folder. So this is your anode side. So this is our zinc being oxidized and losing electrons. And then on the other side, we have our cathode, which is our reduction occurring on that side. Okay, so we have zinc on the left and copper on the right. So what you're going to do is, this is your left hand side, that's your anode. We will put zinc there for the electrode, and then zinc nitrate for our solution. It's already at 1 molar. And then for our cathode side, the right hand side, we have copper. So we will also use that same corresponding copper nitrate, and it's also already at 1 molar. Next, so you have everything correct, just make sure one last time, you will measure cell voltage. Notice that this number pops up here. This is what you're going to record over here on your measured standard cell potential for this particular cell. So you're going to do that for all 3 cells. You're going to set them up and measure those cell potentials. And then from there, you will proceed to the next step, and you will use values in figure 3. So that contains your standard values, and you will calculate your standard cell potential using that, and you will fill those values in here. You will also write and set up your net ionic equation and fill that in here for each cell. If you need some help on using equation 1 with using those values in figure 3 to fill in equation 1, definitely visit one of the pre-recorded videos that I'm linking here. So this is where we left off previously on this lab simulation. And I didn't mention this, but we were on level 0. Now, what we're doing next on part 2 is visiting actually level 4. So we're going to change it to level 4. And notice that these to cell information, both sides, left side and right side, they populated by themselves. So this is a cell generated for you. So you are going to have to notate this information down on, your notes. From this, you are also going to have to generate a cell notation, and then you will also have to calculate a cell potential from this. Okay, so one thing to note is these concentrations are obviously not one the way that they were previously. So we are going to have to use something called the Nernst equation. The Nernst equation is whenever you do not have those standard conditions of 1 molar and 1 atm. And as you saw, we did not have 1 molar for each of those cells. So you're going to have to use equation 3, and you will end up reporting these values here. You will show the data right here, you will show a sample calculation in terms of how you got the data right here. By sample calculation, you can just show for the first problem. You don't have to show it over and over and over for it's the same type of calculation, right? So just make sure to show all your units and everything. Now back to this. So this is one problem that you'll be doing and calculating for. After that, you will repeat steps 4 and 5 for 2 more newly generated cells. You do this by clicking New Problem. One thing you can do that I think is helpful is before you click New Problem is actually going through and calculating your voltages using the Nernst equation and checking your answer. And then you can click New Problem, generates new information, and you go from there. So this is where we left off previously on this lab simulation. And I didn't mention this, but we were on level 0. Now, what we're doing next on part 2 is visiting actually level 4. So we're going to change it to level 4. And notice that these two cell information, both sides, left side and right side, they populated by themselves. So this is a cell generated for you. So you are going to have to notate this information down on, your notes. From this, you are also going to have to generate a cell notation, and then you will also have to calculate a cell potential from this. Okay, so one thing to note is these concentrations are obviously not one the way that they were previously. So we are going to have to use something called the Nernst equation. The Nernst equation is whenever you do not have those standard conditions of 1 molar and 1 atm. And as you saw, we did not have 1 molar for each of those cells. So you're going to have to use equation 3, and you will end up reporting these values here. You will show the data right here, you will show a sample calculation in terms of how you got the data right here. By sample calculation, you can just show for the first problem. You don't have to show it over and over and over for it's the same type of calculation, right? So just make sure to show all your units and everything. Now back to this. So this is one problem that you'll be doing and calculating for. After that, you will repeat steps 4 and 5 for 2 more newly generated cells. You do this by clicking New Problem. One thing you can do that I think is helpful is before you click New Problem is actually going through and calculating your voltages using the Nernst equation and checking your answer. And then you can click New Problem, generates new information, and you go from there. Finally, we have our applied exercises. So here I give you the steps now that you have become more acquainted with this virtual lab. I think it'll be a lot easier. So these are just some follow-up little activities that I would like you to complete. Notice that this is 20 points, so it's about 10 points each problem. And then the previous two parts that we're working on were each 40 points. So those are the main chunk, of work that will contribute to your grade on this lab, because, there's data collection, there's calculations. So just let me know if you have any questions. Definitely check out those supplemental videos that I included. If you don't need them, that's completely fine. If you do need to watch them, go ahead and refresh yourself on certain concepts about electrochemistry.